So let's get started for the app session. And Dr. Prasun Dutta will give the next lecture. It's the third lecture on interferometric detection technique.
All right. So let me remind you where we ended yesterday. First, one thing is that we wrote down an expression which in the left hand side of the expression was V2, which is said we get something which comes from a radio interferometer called visibility. Apparently, you still do not know what it is, but something that comes from the radio interferometer. And it's a function of the baseline and something which I wrote as tau, which I call this kind of delay. And in the right hand side of the expression, there was the H1 power spectrum, which was a function of the variable k, the vector k. So k perpendicular was along the plane of the sky, and k parallel was along the direction of the center of the field of view, line of sight direction. So this is kind of we set up the coordinate system. If I am looking at this patch in the sky, then if I consider a vector that goes through the center of that patch, the patch is called the field of view. I call that direction n0 cap. Remember, for any direction you need you are living in 3 dimensions. I call your direction, so that is 2 numbers. So that n0 will be given by 2 numbers. And as the earth rotates, the sky apparently rotates around us. What these type of observations do is it follows the sky. Its n0 cap is always at a given direction in the sky, that is at one area and depth. Around that, you not only observe in that direction, but you observe around that. So if I consider another direction which is inside that small field of view, I call that direction say n cap or n1 cap, depending on my preference. If I assume all the signal is originating from very far away, from the inner surface of a hemisphere, I call the radius of that hemisphere r. This r you can think of as the co-moving radius to that distance, if you wish. And then the signals are originating, so differential part of the signal. So what I will do is I will try to figure out the entire signal from this region, but then we'll start with a small region which I call dr. And because it's a 2-dimensional patch, the measure of that dr will be r squared dn cap. And then I have, if I wish, some point I may need a 3-dimensional Cartesian system. This Cartesian system, the z-axis is along n0 cap, and then I will have perpendicular plane which is x cap y cap, which lies in the tangent plane at that point in the sky. This x cap is usually chosen as we said along its h to h direction, y cap along north-south direction, and then you go right-hand coordinate system. So this is the setup, and let's assume that I have one antenna to detect this signal. This antenna I call the antenna A. In this coordinate system, where I have chosen the origin at somewhere on the earth, the distance to this antenna is xl. Vector that goes to the antenna is xl. You can hence you can decompose the component of this in this system if you wish. Now, what we want to do is that we like to go through what is called the Van-Citer-Janicke theorem, and I think that most of you have already done it. But then we will see that Van-Citer-Janicke theorem is obviously an ideal case. We will go through this kind of signal chain, and then see that what actually we measured instead of what we call the visibility in the Van-Citer-Janicke theorem. What comes from the sky is an electric field. Because we are measuring in radio wavelengths or radio frequencies, we can actually measure the electric field as a function of time. What is the frequency in which we are interested to measure? So even if the redshift is 0, it is 1420 megahertz, like 1 gigahertz, around 1 gigahertz. Say I don't want to measure radio signal, I want to measure say optical signal. What will be the frequency? 10 to the 14, 15 hertz, right? So if I ask you to measure the electric field of an optical signal, there is something called Nyquist sampling theorem, which means that to get the property of that signal, you have to, within one time period of the signal, you have to measure it at least twice. Right? So if it is 10 to the 15 hertz, for example, you have to measure at the order of 10 to the 15 hertz. Every 10 to the 15 seconds, or every, you have to measure 10 to the 15 times in 1 second. And then you have to record that signal. Is that possible to record a signal at 10 to the 15 hertz? In your computer, for example, your computer has a clock speed of say 5 gigahertz. Too small for that. But for radio, you can do that because 5 gigahertz is already 5 times 1 gigahertz. Anyway, yes, the 5 gigahertz is not the limit, but that was just to give you an idea. So here I can actually measure the electric field. I can measure the electric field, record it as a function of time. So that electric field originates from the sky, and something happens to it as it passes through the universe. That something happens. What happens to it as it passes through the universe? We have been learning it is called the radiative transfer of radiation from where it originates. You see, the first time it gets modified, not because of anything other than Earth, is the ionosphere. So the ionosphere, which is not quite transparent to the radio wavelengths, changes the signal. So you have to see what the ionosphere does to the signal. Then after ionosphere, it comes to the antenna. Then the dish itself, all the dipoles that sits at the focus of the dish, does something to the signal. Comes with electronics, essentially records the signal to the computer. So does something to the signal. Eventually, here is what you get, which we call some number which is proportional to the voltage. I'll call this voltage. Now, if it is just any other observation other than the observation of 21 centimeter radiation from Epoch of Reionization, etc., I could have said that all these effects can be get rid of using some type of calibration technique. Okay. But we will see that because we are dealing with a radiation which is faint, plus at the same frequency there is another radiation or another set of radiation which is much higher than the 21 centimeter radiation, the so-called foregrounds, to originate between the sky and the ionosphere here. So that is like 10 to the 3 or 10 to the 4 times in visibility, which means if I want to measure the power spectrum, it's 10 to the 7, 10 to the 8 times. Very large. Now, when you are trying to measure two signals, so let's say that I want to measure one signal, okay, which has a maximum amplitude, say 10. The noise that I have in my system is 1. Okay. I say that I need a dynamic range of my detector which is 10:1. 10. In this case, I want to measure a signal which is 10 to the 7 times the other signal. Means I need at least 10 to the 7 as my dynamic range. That is, I need even more because I want to finally see the variation in the 21 centimeters. It's a high dynamic range problem. That is the thing that because of which we actually need to go back and look at what are the assumptions that goes in the Vansittart-Janicki theorem and need to figure out what exactly it is instead of just using the textbook thing. Okay, so let us start with the signal at the source. So the way we will proceed is, first we will assume there is no ionosphere and all. We'll just write down the electric field just before the antenna if there is no ionosphere. Will be that electric. Call it E. The E is measured at the antenna position A, XA. Right. Now, if it is measured at antenna position XA at a time t, and it is coming from the source somewhere, must have traveled from there to the antenna. So how do I travel? How do I make an electric field travel from one place to the other? What is that in optics that you have learned? Tells you if the electric field at the source is E, originating from that small patch in the sky which I call delta R1, then what will be the electric field at the antenna? It's called Huygens propagation, right? That's one of the ways you can approximate is called the Huygens propagation. So this will be the electric field which has originated at R1, but then cannot be at the same time at which it detects. Must have originated earlier, right? So this should be T minus the distance between the antenna A and the place which has originated divided by C. So this has to the retarded electric field so far. And then if you remember that the tunnel by which I have to propagate it, so this is the electric field this time, this is the electric field there at the source, so I have to have 2 pi by lambda times the spherical wave by dA by lambda. Here is the, so let me write down what is dA here. What is dA? Here the vector dA is R1 minus X. Which special relativistic effect? Yeah, so this is a retarded time T minus dA by C. There is no source is not moving anywhere. Source is there. Which one? dA is length. So, so this stands. So there are two R here. R squared. I have one length here, one length. Okay. Now, so this is, as I said, this is if we don't have the ionosphere. What does the ionosphere do? Why? Right. So there is a refractive. The ionosphere is not transparent. Not transparent essentially means that there is a refractive index which is not equals to 1. And then if there is a thickness of the ionosphere is something, so then you will get a phase because of that, which is dl times the refractive index. Right. Now this is a phase that will be added. But then there will be a delay as well added because of the ionosphere, and unfortunately I will not write it. In the delay wish, just write the phase factor. Now what that phase factor will depend on? Think of, so I have this antenna looking at this direction, and I have an ionosphere. This is. And imagine that I have another antenna looking at the same direction in the sky, which essentially means that these two lines are parallel to each other. First thing you realize that it will depend on the position of the antenna. Right? This will depend on the position of the antenna. And because I am leveling the antennas as A and B, so I will just write an A over there. But that A essentially means that phi depends on the vector x-ray. Okay. What else does it depend on? Obviously, if I look at this direction, it will go through a different patch of the ionosphere. So it will depend on, can depend on the direction I am looking at. And for corresponding to R1, the direction is N1. And it may change with time.
What is that?
Refractive index. You can use whatever you want.
Two things. One is the delay and the other is the phase.
Right. I have not written down the delay. So there should be a delay also. I have not. For this lecture, I am not considering it.
The delay corresponds to phase delay or phase.
Delay corresponds to if I am observing at a frequency omega, then it takes a little bit extra time to come through this. That extra time, whatever you call it, there will be a phase because of that. But anyway, so I am not writing it down. There is a reason for it. And then when you try to look at the frequency dependence of this is not incorrect. This is correct. What I have written down here. Actually, the delay part is already there in this page. But to extract it out, I will not do it. That you can try to do yourself. Okay. Now what is there after this? After the ionosphere, that is added. I have the antenna, right? And again, the antenna, as I said last time as well, looks differently at different directions inside the field of view. In fact, the field of view is there because the antenna looks differently at different directions. At this direction, the antenna receives the maximum and then the reception goes down. So I will put in a factor now, which I will write curly A. This is to distinguish from the capital A that I wrote down last time, because the capital A was the thing which was multiplying the intensity in the sky, right? This is not multiplying the intensity, it is multiplying the electric field. Square of the electric field is proportional to the intensity. So now what will this be a function of? This obviously depends on which antenna you are looking at. So I'll put an A over here, so that corresponds to the antenna A. It will definitely be a function of n cap or n1 cap, because that's the notation I am using. Can it be a function of time? Yes or no? Right. What is this? The antenna beam pattern. Okay, so let's tell you why it will be a function of time and why it will not be a function of time. Why it will not be first. Okay. Let's assume that the antenna beam pattern does not have any azimuthal dependence. It does not change along this direction. It only depends on the distance from here. Then it will not be a function of time. Okay. But if it has an azimuthal dependence, which means it not only depends, it depends on both the directions. So this n cap I can write in terms of theta and phi. So that it does depend on both theta and phi, not only theta. Then there is another effect that happens. If I look at a part of the sky, this is a part of the sky. It's not a part of the sky my antenna is looking at. It's a broader part of the sky. Okay. And you can imagine. So let's say that I have the Orion here. Okay. If I look the Orion at a different time, the Orion will okay. Right. Now, if I want to look at this part of the sky, so this is, I pointed my telescope there, so this is my telescope field of view. Now in this field of view, because it is not, as I said, it's not symmetric, so let's try to prove some asymmetry over here, like this. What happens is, because of the way the antenna operates, this pattern rotates. You see, with respect to order, is something you are looking at. The direction of this asymmetry has changed. With respect to order, with respect to the side, this will pick up the time dependence. This is the case of almost all the antennas. In case of things like geometry, you can think of these as the structure that holds the dipoles at the top of the antenna. Yes.
You're assuming if the alt-azimuth mount is
You are assuming as an alt-azimuth mount. Most of the telescopes are like that. It's not like the mount in the next row. That's the equatorial mount. If it's an equatorial mount, it will not work. And then even in alt-azimuth mount, there are telescopes called ASCAP, which actually rotates the feet such that it take care of this type of thing. But anyway, so that it is. But mostly it can be there. All right. What else? What else? Right. Now, so after this we have the electronics. What the electronics will do is that it will add its own gain. The gain will depend on which antenna you are looking at. But it will not definitely look at which direction. The electronics doesn't care about whether you are looking at this side. It will be only a function of theta. So by the time you detect it as this, and then if you really wish, you have a random noise added to this. The characteristics of the random noise may depend on which antenna you are using. Any questions so far? Yeah.
I five variable to the I five. That was integral dl times the refractor.
Whatever it is. So I don't care whether n changes or L changes, the entire effect is there.
What is the dimension? Again, has two dimensions, yes, right. How can it be 2 pi by lambda?
There is 2 pi by lambda. So that's why if I am interested in this, I really am not interested in the exact details of. So NDL is the path difference, so to change it to phase difference. Okay. One thing is missing is in this entire expression. What is it? Which frequency are you observing? There's no frequency dependence in anywhere. Why? Because when you observe this electric field, you actually sample it at very high delta t intervals, and you have to extract out the frequency information from here. It is not there as you observe. Now, there are two ways the frequency information is extracted out. So I will talk about one way where what you do is that you do a time Fourier transform of this signal first, and then you correlate signals from two different antennas. So this type of ways of extracting out the frequency inference and the visibility is called FX correlation. F for Fourier transform, X for correlation. But so how do I do that? Well, if I look at most of these where I have the frequency dependence, I have a frequency dependence here, I have a frequency dependence here, here, here. This is just a random number. Care about it that much. Amongst all these frequency dependence, this is something which changes at 1 gigahertz, around that. Right? So it changes every 10 to the 9 times per second. But electronic gain or this doesn't change that fast. Which means what I can do is I can do an integral. Let me write it here. I can do an integral t tau by 2 t plus tau by 2 and So I do this integral. At that, so this tau by 2 is chosen like, so tau is chosen like 1 by 2 times the bandwidth of my measurement, or lower. Okay, at least this, or lower, less than. That's called the Nyquist-Shannon sampling criteria. If I choose like this, then okay, let's see that my bandwidth I want to observe say 32 megahertz band. Okay, so which means that tau should be less than equals to 64 megahertz. So I should measure 64 into 10 to the 6 times per second. For each such measurements, these things literally does not change. Atmosphere electron density does not change so fast. The gain, electronic gain doesn't change so fast. This doesn't change so fast at all. Which means when I do this integral, the things which doesn't change so fast will just go out of the integral. What will remain is this, which depends on the frequency. Which will, so what will I get if I do this? If I do this, as I said that everything else goes out of the integral. So let me do one more thing, which is that I club this with say that it's just a number, club it with GA. I call that entire thing as G as a function of T. And then when I'm saying that I am writing it this, does this look like a Fourier transform? How many of you think it is a Fourier transform? It's not a Fourier transform because these integrals are not minus infinity to plus infinity. How do I make it a Fourier transform? I can write it as minus infinity to plus infinity dt prime e to the I omega t prime. Not a vector E. It's a E. And then this effect I can write as a window, which is a window between. So let's just write it this way. Give a convolution E minus T. This is just that integral. You see that after you do the integral, it will be a function of T. So that T prime is integrated over. This is called a bandpass filter. And now if I write this entire signal in terms of electric fields, now I have to put in both omega and T here. Let's see how it will look like. This entire thing I have written already as GAT. That bandpass filter, Fourier transform will come in, and in principle it can still have a small time dependence, so I'll just keep it in, or you can forget about it. Maybe that is also in. So this is just this. The only other thing that supposed to change is frequency was this, so this will pick up the frequency dependence. The rest of the things will remain as it is. This will change a little bit. Will be some other random numbers here. Is it some random noise added? Any question here? Which one? So I'm writing down this quantity. That is in the left hand side now. Okay. This quantity will be what? This XA omega, and see there is a slow time dependence. This thing changes slowly with time, right? This and this. That slow time dependence will still remain. And then this is a convolution relation. The Fourier domain, it will be a multiplication. by VA is a Fourier transform of that. That I have now clubbed in there. Now, they said that only this thing changes with frequency. That's not quite true. This also changes with frequency. This also changes with frequency. There is a fast. See, what do you mean by that something has a frequency dependence? Essentially means that if I have a time domain signal means signal will change with time. It's some signal, A omega. A is already there, so small a omega. If this looks like that, it has a frequency. Right? If it looks, what do you call? Say that it has a fast frequency variation and a slow frequency variation. The time domain signal may also look something like this. So there is a slow time variation, which is that line, and then on top of that there is this fast variation. The fast variation I can ascribe to a frequency. Slow variation will still be a time variation. So that's what is happening for this entire thing. So these are still a time variation, but there can be a faster variation in these things as well, that I will call the frequency. Okay. Any questions so far? Because now I have the voltage that is recorded by one antenna, or only that small patch in the sky. Now I have to integrate over the entire sky. Yeah. Lambda is just a number, right? The observing wavelength. It corresponds to a frequency, but if I fix to one frequency, it's just a number. Then I am looking small, very fast time variations. See, any electric field is a function of time. If I take a region of the electric field and do this integral, I may pick up some frequency because of that. That is how I say that this time variation has a frequency. The frequency is a periodic variation in time, right? So it can have larger frequencies, lower frequency, etc. Here I have two types of time variation. One is happening at some gigahertz scales, another is happening maybe second scale. I'm separating those out. If I do an integral where the tau is few gigahertz, then the second scale variation will come out of the integral, because I'm doing it at every second, for example, or every millisecond. So the second scale variation will not affect the millisecond integral. Those will come out of the integral. Right. 100 and 150 is very close by. 100 megahertz and 150 hertz. Yeah. Lambda will change, but lambda corresponds to 100 megahertz. It does not correspond to 150 hertz. Only 100 megahertz.
So the variation of 150 to 100 plus 150.
No, right. See, I am talking about all these things. I have a time domain signal. Okay. So this is, let's say, because you are interested, so let me put in a omega 0 here. There is C as a function of T. There is a D as a function of T. This I call slow, because this changes at say 1 second scale. This I call fast. This changes at 10 to the minus 6 seconds. this is just a number. Does not change. This doesn't change with time. Like lambda was, if my telescope is the central frequency of the bandwidth is some mu corresponding to that. That is a lambda. That is. Now, if I integrate this, forget about Fourier transform. If I do it, t is a t prime, right? So t minus 1 millisecond to t plus 1 millisecond. What will I get here? 1 by 2 milliseconds. This is an average of the signal over 2 milliseconds. If there is an oscillation at 1 microsecond, that will cancel out. Right? This will not give you anything. So let's say this is plus that. So this will go to 0, that integral. This will only be omega 0 times. That's exactly what we're doing. This separation of fast variation and slow variation is the entire game of calibration as well. It can be done. Those fast and slower variations have a certain amplitude relation. The amplitude of the variations are related in a certain way. Anyway, so that will count. When I have this signal,
Tau should be less than slow varying time.
tau should be of the order of the variation of the first one. Should be much less than the slow varying time. Much less. So that you can take that. So I do the integral now. This integral is over all directions. Okay. This integral is over all directions, and then where is the measure of the integral? So here is the measure of the integral. So for the time being, let me forget about the noise. I can put that back in. Let's say after a random number, I can put that back in at my view. So this is r squared dn1 cap. So that was dr. So that is the electric field. I should have written delta E over here because that is coming from that small patch of the sky. Now this is the total electric field recorded from the entire sky. The other thing that you can take out of the integral is this, because that doesn't depend on n cap. See, everything else depends on n cap in certain way. dA also depends on n cap, because what is dA? dA is R1 minus XA. R1 has the n cap dependence. Okay. Everything else depends on n cap. Now, we want to do this, that phi A, said it depends on n cap and P. But I can always write this in terms of some phi A0, which depends only on time, then the n cap dependence in terms of call that phi A itself. Basically, what I am saying is part of the ionospheric phase may not depend on which direction you are looking at. It's average everywhere. And on top of that, there will be a direction dependence. All that you are doing is have this thing, and which is the ionosphere. So whatever direction I am looking at, there will be some part of the ionosphere that I am taking out, the average thing. Then the extra thing is what I am calling phi A. Why I am doing this? Because this thing can be clubbed within this GA, because it has the exact same dependence. I don't care where it is coming from, but it is something which depends on which antenna and the time. This is also something which depends on which antenna and the time. Okay. So the gain, they call the electronic gain, can have a part from the ionosphere which is independent of the direction. So that I can take out of the integral. Okay, omega T. Now, call this keep that GAT over here. Remember that these things can be complex, because these are gains multiplying a complex number to it. They can also be complex. So that I have written down there. Now this phi A doesn't depend on But this phi a is this excess part. Phi a is the excess. Now, if I look at the antenna beam pattern, again this can have an isotropic part. It depends on n cap, right? And then it can have a time dependence. There can be a part which depends on n cap. Then there will be a part which depends on both n cap and okay. This you can think of as an isotropic dependence on n cap. Remember that n cap I can write in terms of theta and phi. So this is my field of view. Theta is the angle that changes in this direction. So if I am looking from there, that is the theta. Phi is the angle which changes in this direction. So that A1, A0, n cap is independent of phi in all directions. And that you have to think. To give you a theta dependence, because this moves across the sky, this thing rotates the cycle, spokes rotates, will also be a time dependence, so that I have to keep. Now again, if you look at this looks like a term like this. So this A10 is also a function of N1 cap and theta. Right, just like that term. And then this A0 is only a function of n cap. So what I will do is, simplify this expression. You have been collecting where different terms are coming from, but now let's start to forget them. This club things which has the similar types of dependencies. So I have this GAT, which now has dependence from the electronic gain, also the isotropic dependence from the ionosphere. Then I have the biannual term. Let me write d n cap here, and that's r square which take out. These two combined, I will write with tilde curly d, which is a function of n cap and p. And the rest is c r omega p minus dA by c. I think that's it. Right? That is the electric field detected by one antenna. If you are doing single dish radio astronomy, the thing that you detect is square of mod square of this. Intensity as measured by a single dish is mod square of this. Any questions? Okay. So one thing I forgot is that remember I have multiplied by the gain. So this really is the voltage. That's the voltage, not the. Once I multiply by the gain, it's the voltage that is recorded. Now, in radio interferometry, which essentially means that I have to correlate the voltages recorded at two different antennas. That's what you do. correlate the voltage is recorded at two different antennas. I'll call that VAB. So it is the voltage recorded from antenna A, voltage recorded from antenna B, omega P. Now I'm skipping one step here. So when I say correlate, what again I do is, how do I correlate? Yes. This one. So remember I had to the I phi A, and then I have A, which I forgot to write first. There is another A. The function. So I have this as a function of time as well. So this was something, the other thing was something which is a function of encapment time. This was the e to the power phi a was also a function of encapment time. Those two are common. Very important. This is the omega t star the ensemble average. Now in real life, this ensemble average is done by a time average again over a certain time scale, but I'm skipping that. Now once you do that, so I have to put in this two times, right? A huge thing. I'll not do that. But once you do that, what are the things which is changing fastest in this? Which time? Again, the changing thing which is changing fastest is the C. So the ensemble average of the C just writing it this way is R squared, a two-dimensional Dirac delta function on R1 minus R2 and the intensity. Why is it so? Because what I have to do is I have to correlate the electric field at two different places. One is at R1, one is at R2. Now what are R1 and R2? R1 and R2 is two different points in the sky. Now these two different points can be as close as your resolution beam. And when you are looking at cosmological signal, they may be few parsecs away. Electric fields coming from two different, one parsec apart. If you ask them to be correlated at one parsec apart, then you are thinking of a signal which has a correlation length of one parsec. It's too big. We'll say that it's not correlated. It's only element when they are coming from the exact same direction. So if I do this, let me write down what I get. And I'm skipping one thing here, which is fine. Sorry, this is actually minus 2. So I have this dA in the denominator. So they are approximately equals to RA, approximately equals to R. So two of them will give you R square, and then there is R square there, so that is a this R4. That essentially happens. What you will be left with, so I'll just write this down. Okay. Assuming most of you have already done Nancy-Janicke theorem, the step that involves is already done in fancy design, so I will not do it again. So this B is, let me write this at least. So this is XA minus XB by lambda. And you can see, so this is pretty one. All the gains are 1. These are all 1. DADBs are 1. So then it is just the Van-Cittag-Janicki theorem. I have one more thing, which is the A. Now this A as n cap is modular square of that. Okay. So if all the gains are 1, so then this is essentially Van-Cittag-Janicki theorem. But all the gains are not 1. Let's see what are the factors for the gain there. So there are gains which depend on time. There are gains which depend on frequency. And then there are gains within the integral which depends on the direction you are looking. Okay. If these things are not there, then the rest of the things from the integral you could have called the visibility. But because these things are there, the thing inside the integral is still not the visibility. So I have to address the effect of all of these separately. Any question? Few steps gone into from there to there. Reconstructive.
Can we calling it B as a scale?
Because that's something that multiplies your rest of the visibility. These are 1. This is 1. This is 1. The rest of it is visibility. Changing it from 1. That's some effect which is coming because of the instrument and the ion square. That's right. Okay. So let us now the effect of these are taken care of by two methods. One is called primary calibration, which is done every say 30 minutes or 20 minutes, assuming that these things doesn't change in 30 minutes or 20 minutes time scale. To do primary calibration, you need to any calibration you need to have a standard thing, right? Against which you calibrate. For primary calibration, you observe some source for which you already know what is the intensity, or you already know what is the visibility. Okay. And you neglect the fact that there are these direction dependent gains. Fortunately, the effect of direction dependent gains are smaller compared to the effect of these gains. What one can do is, you can do things iteratively. You assume that these things are 1 and try to find out what are these. And once you are confident enough on what these things are, you can go back and try to find out what are the direction dependent gains. Now, finding these also done in 2 steps. One is, as I said, that every 20 minutes you observe a calibrator source and you calibrate the gain, which is the change in this quantity at 20-minute time scale, for example. Then, once that is done, you have some idea about what is the sky. And that model of the sky exists all the time. Because in between, so what you do is that you observe for a calibrator source, and then you observe for the target source at 21 centimeters. Again, you observe a calibrator source, and then again 21 centimeters. Calibrator source. Time is 20 minutes. I'm just cooking up this number of the same order that you are observing at 150 measurements. Now, you calculate the gain here, gain there, and then interpolate between. So once you interpolate, you have some idea about these gains and this region. And then once you have some idea about this gain, you correct for that, you get some idea about the visibility. That is this region, which is your 21 centimeters. Now, you use those to correct So you use those to make a model of the sky. Once you make a model of the sky, now that model of the sky works as the standard source for calibration. Calibrate against that model. So it's a self-calibration. Okay. So that will now, so because the model of the sky exists, the time interval that you want, you can now calculate for the faster, correct for the faster time scale. Okay, so that's called self-calibration. Anyway, so I will stop there, and then next time we'll talk about the direction dependent calibration and the other things that is important in this. Any question you can still ask?